Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to calculate the centroid for a three-dimensional homogeneous geometry here. So what we're looking at, imagine this curve here defined by the following function here, y squared equals 2z, sitting on top of this x, y, z coordinate system. This is a standard right-handed coordinate system. Notice that if I take I cross j, I still get k. And what we're going to do is try to figure out the coordinates of the centroid, x bar, y bar, z bar, for this geometry. Now, x bar and y bar, I'm just going to do this. By symmetry here, x bar has got to be 0, same thing with y bar. The coordinates of the centroid are somewhere in the middle here. And notice, it's 2 meters from here to here. There's a lot more volume. If I cut this in half and I look at 1 meter up, there's a lot more volume apparently above it than below it. So that coordinate is of the centroid there, that guy right there, is probably something like about 1.5. All right, so now we got to figure out how to calculate it. So if you watched my previous videos on this, trying to find centroids, you can find them various ways. So, for one-dimensional problems, you break the problem into little ds's, and then you've got x times ds. And then you add these all up and divide by the total length. So in that example, you would be finding the centroid as a weighted average, using length to weight it. Sometimes, when you got a function, you're breaking it up maybe into rectangles. And the coordinates of this rectangle here might be something like x and y over 2. And then you take the x coordinate of the rectangle times the area dA, add those all up, and then divide by the total area. So in that case, you'd be weighting x against the area. Well, sometimes when you got three-dimensional geometry, like in this example, what you want to do is use volume to do your weighted average. So what I'm going to do is I'm going to break this curve up into a bunch of little slices. So I'm going to imagine one of these slices. See if I can draw it here. There we go. Alright, so I'm going to imagine a little slice of this curve that's kind of looking like this. And just to give it kind of a 3D look to it, something like that. Now it's important to realize what we're looking at here. What we're looking at is a disk. This dimension right here is going to be a dz. The centroid of the disk is right at its geometric center. I'm going to put a red dot there. And again, that's meant to be at the centroid of this disk. The coordinates of the centroid of the disk are 0, 0, and z, whatever that is. Z being this dimension right there. So what we can do to find the centroid of the three-dimensional geometry is we're going to average these. So you got to picture a whole bunch of these disks up and down. We're going to take z, right? That's the coordinate we're trying to average, and we have to assign it a weight. I'm going to do that by multiplying it by the volume of this disk. The volume of that disk would be equal to pi, for now I'll just put r, pi r squared dz, where the r is the radius of the disk. Now, so we've got z, which is what we're trying to average, times the volume. Then we're going to want to add these all up. Now, if this integral ends up over z, that's going to run 0 to 2. And then what we'd have to do is divide out the total volume. So this expression represents the volume of the disk. We would have to add those all up. Pi r squared dz, which again is going to run from 0 to 2. So this integral divided by this integral should give me z bar, because again we are averaging the z coordinate of all these little elements. And now it's just a matter of working out the integral. Now this point right here, this distance on this graph is the radius, but it's also equal to y. So r and y are the same, and y squared is equal to 2z. So when I work that top integral, we're going to have the integral of z times r squared Okay, now r and y are the same, so we could say that's y squared, which is 2z. And then there's a pi, which I'll bring out in front, times dz. And I'll go ahead and get this integral finished, and then I'll do the bottom one. And again, we're going to run that 0 to 2. And it's a reasonably easy integral here to work out. We're going to have 2 pi times the antiderivative, or the integral of z squared dz. That's z to the third over 3 from 0 to 2. And that's going to give me a moment here. I got 16.7 out of that for a numerical value. I'll just look at that one more time. Okay, I ran it again, got the same value. So remember, this was the top of our integral. Now we're going to work the bottom. So now in the bottom, we're going to have the integral 0 to 2. Right, that pi might as well just come out in front. R squared, and remember the radius here and y are the same. So r squared is 2z. The 2 I'll bring out in front. Z dz. So we're going to have 2 pi times z squared over 2 from 0 to 2. Boy, that one's kind of a nice one. These are going to just cancel. So that's going to give us pi times 4 minus 0. I get 12.56 out of that. So our z bar, remember, is our top integral, 16.7, divided by our bottom integral, 12.56. .3, about 1.3, maybe 2, let's say. So here's an example of how to find, or how to use a weighted average to, in this case, find the average z value. And again, the idea is to break this thing up into a whole bunch of these little disks. Right? These are the disks I'm talking about right here. And then we're averaging the z coordinate of that disk, because we're trying to find z bar, because x bar and y bar in this example would be known due to symmetry. The important thing is how to weight it by area. So you multiply by the area of the element, divide by the total, I'm sorry, did I say area? I meant volume. In this case, we're weighting it by volume. That represented the volume of this element. And therefore, our bottom integral, we have to divide out the total volume. So again, with these centroid problems, sometimes you're weighting it by a one-dimensional thing. If it's a one-dimensional problem, you're breaking it into little ds's. If it's a two-dimensional problem, some sort of curve, you're typically looking at rectangles. And then you're giving the centroid a weight by the area of the rectangle, and then you divide out the total area. And sometimes, like this example, you're looking at a three-dimensional problem where you take the centroid variables x, y, and z, and you give them a weight by volume, just like I've demonstrated here. So hope this video helps demonstrate how to do these things. Oh, let me quick go back and comment about the 1.32. Remember that I had guessed about 1.5. So again, that doesn't prove it's right, but it's, pretty reasonable evidence. The odds that we could go through there and make a significant math mistake and still get something really close to that 1.5, give or take a little bit, that I was looking for is pretty low. So I got a lot of confidence in that result. Hope this video helps demonstrate how to do these calculations. Have a great day.